The stars have lives. They are born, they live, and they die. How a star dies depends upon its mass, as this dictates the squeezing due to gravity and consequently the rate of nuclear reactions at its core. This means that some stars can end their life in a bang, but for many, it is more of a whimper. As we have seen, these stars can end their lives spectacularly in immense supernova explosions that can be seen across the universe. Here, an entire star can be ripped apart by the push of the uncountable, ghostly neutrinos. As a massive star ages, nuclear burning in its core continues until iron is produced. But iron is different from all the other elements that came before it in the star's life cycle, and fusing iron into heavier elements actually sucks in energy rather than emitting it. Suddenly, the nuclear fires in the star's core are switched off, and the outward push from radiation vanishes. There is nothing to prevent gravity's inexorable squeeze, and the star collapses down on itself. The density soars, the temperature soars, and as iron gets forced into heavier elements, the end burst of neutrinos is released, and the star explodes outward. Well, not all of the stars. As the density increases in the very core, so does the pull of gravity, accelerating further collapse. At some moment, a critical point is passed, and nothing can stop the inward pull of gravity, and a black hole, usually several times more massive than our own sun, is formed. This black hole is the remnant of the massive star, surrounded by an expanding and fading shell of debris from the explosion. For slightly less massive stars, the process is very similar, but while the density and gravity can soar in the collapsing core, they never reach the critical point to form a black hole. The collapse can be halted, but this only happens after electrons are squeezed into atomic nuclei and into protons, creating neutrons. The resulting star consists entirely of neutrons. Such a neutron star is an extremely weird place, like nothing on Earth. The death of a less massive star, like our Sun, is less dramatic. The Sun is roughly halfway through its expected 11 billion year lifetime, and as it approaches its end of days, it steadily changes its internal consistency as heavier and heavier elements are forged. The Sun doesn't have the gravitational squeeze to create elements like iron, but its changing internal structure will cause it to swell to an immense size, becoming a red giant star, ultimately consuming Mars. Its unstable nuclear reactions will cause it to pulse more and more violently, blowing off its outer layers and leaving little but the stellar core. This dead core of the star, known as a white dwarf, will be the extremely hot and dense remnant of the stellar heart. It will be about the size of the Earth, with the mass of about the Sun, but it will no longer be able to sustain any nuclear reactions. Its heat will provide an outward pressure that can hold gravity at bay, at least for a while. While born hot, this white dwarf star will eventually begin to cool down, and over many billions of years, will fade to be as cool as the background universe, a truly dead star known as a black dwarf. The time needed for a white dwarf to cool down to the background temperature of the universe is immense, many times longer than the current age of the universe, so no true black dwarfs may yet exist. But they will be there in abundance in the future universe. We should complete this story and consider the lowest mass stars. These, the red dwarfs, are the most numerous stars in the universe today, and their ends will be completely undramatic. Due to their low masses, their nuclear reactions are sedate, burning slowly and steadily for more than 100 trillion years. But once the nuclear fuel, the hydrogen in their cores, is exhausted, there is little more these tiny stars can do. They simply go out and fade into the darkness. Once dark, dead red dwarfs will still retain a bit of heat, providing a little pressure to prevent collapse. But they too will eventually cool, losing all energy into the darkness of the universe. But there is something puzzling about these dead stellar remnants. After the outward push from nuclear reactions or the pressure of heat is gone, why don't they all succumb to gravity's immense squeezing and collapse into black holes? You might wonder if they are like the Earth, which is not collapsing even though it is not supported by nuclear reactions at its core. In the Earth, it is the electromagnetic attraction and repulsion of atoms that can overcome gravity's squeezing, providing enough push to prevent collapse. But dead stars are much more massive than the Earth, with much stronger gravity overcoming the pressure provided by electromagnetism. So where does the force that prevents their gravitational demise come from? Looking at the early universe found that deuterium was a crucial building block of matter because other options like diprotons and dineutrons were unstable. This instability was due to their spins and the nuclear force. The Pauli exclusion principle said that no two fermions could be in the same state, meaning they couldn't have identical wave functions. Now, in simpler terms, fermions, like deuterium, can't be in the same state, while bosons, like photons, can. Photons, for instance, can gather together in things like laser beams. When bosons come together, you can think of them as one entity with a single description. But we don't want to talk about bosons, since most matter is made of fermions. Fermions do not condense to occupy the same wave function, a consequence of the exclusion principle. Pauli introduced his idea as an accounting mechanism to explain why electrons seems to arrange their energies in the odd way they do, as is easiest to see in the patterns in the periodic table. The idea was quickly elevated to a principle from which one could derive the arrangement of electrons in atoms once spin was introduced. At the time, it was understood that higher energy electrons spent their time farther from the nuclei of atoms. An atom with either high energy or a lot of electrons thus occupies a lot of volume, relatively speaking. The fact that higher energy electrons occupy more volume had already been measured in experiments. Shortly after Pauli introduced the idea, Paul Ehrenfest pointed out that going in the opposite direction has interesting consequences. If we try to condense atoms, the electrons get pushed closer to the nuclei to occupy less volume. But the Pauli exclusion principle forbids this, as these electrons cannot share wave functions. This application of Pauli's idea demonstrates why mass has volume at all. Perhaps, though, you preferred filling the orbitals of atoms with electrons to dissecting frogs. The exercise, of course, turned into one of rote memorization, though a few mnemonics exist. The key task was to remember when to pair electrons with spin down with electrons with spin up, a task disguising the Pauli exclusion principle. In the lowest energy level, 1s, only 2 electrons were allowed. One would have spin up and the other spin down. Yet spin, you'll recall, is an internal degree of freedom not contributing to the overall energy of the electrons in an atom. 2 electrons can have the same lowest possible energy so long as they have opposite spin. In other words, fermions can have the same energy without sharing wave functions. The terminology for this in physics is degeneracy. The Pauli exclusion principle requires that no 2 fermions share the same set of values for all observables. However, they can share all but one value. The most obvious values are imported from our classical intuition, things like position, speed, energy, etc. Fermions are free to share all these so long as their internal quantum degrees of freedom are different. This is why 2 or more electrons in an atom can share the same energy level. The lower the energy, the less degenerate it is. Since the lowest energy level in an atom, 1s, can support only 2 electrons, 1 spin up, 1 spin down, the remainder of the electrons must possess higher energy. Thus, even cooling atoms to absolute zero results in electrons with high energy. A cloud of electrons, called a Fermi gas on account of them being fermions, resists compression precisely because of the Pauli exclusion principle. A resistance to compression is otherwise known as pressure. To distinguish this from the pressure caused by heat in a normal gas, we call it degeneracy pressure. 2 masses, be they atoms or planets, are attracted to each other through the force of gravity. When one of the masses is very big compared to the other, we often think of that mass as being fixed in place while the other either falls into it, escapes off to infinity, or orbits around it. For example, the Sun accounts for 99.9% of the mass of the entire solar system. This means the center of gravity of the solar system can be taken to be the center of the Sun, for all practical purposes. The regular motion of the planets around the Sun is a result of the enormous size of the Sun compared to that of the planets. When the masses are of comparable size, the motion becomes more complicated. Pluto's moon Charon, for example, does not orbit Pluto as our moon orbits Earth. Charon and Pluto orbit the center of gravity of both their masses, which does not lie within Pluto. They are in a perpetual cosmic dance around each other. More objects have very complicated, technically chaotic, behavior. However, even if their trajectories are not simple circles or ellipses, they all still orbit a center of gravity, and as they lose energy, they fall toward that center of gravity. This is how things get compacted, how stars and planets form. Gravity is always pulling things together. But if gravity were the only force, everything would end up as a single gargantuan mass in an infinitely small point. For a star like the Sun, something must counterbalance the force of gravity to give it shape. As the Sun burns hydrogen into helium, it is the outward pressure from the radiation flowing from its core. But once this is gone, gravity will compress the core until degeneracy pressure stops it. This is the pressure that stops dead stars from collapsing into black holes. Once our Sun becomes a white dwarf, it will be a Fermi gas of electrons with helium and carbon nuclei swimming about. This will support this remnant of the Sun as it loses its heat and cools into a black dwarf and beyond. For stars larger than the Sun, the extra mass causes more force from gravity, compressing the white dwarf to an even smaller size and forcing the electrons to have even more energy. But there is a limit. Electrons cannot have so much kinetic energy that their speed would be faster than light, the speed limit set by special relativity. Physicist Subrahmanyan Chandrasekhar calculated what this limit would be in terms of mass. The Chandrasekhar limit, as it is now known, is about 1.4 times the mass of our own Sun. For a star to have left a core of this size, it would have been about 8 solar masses during its lifetime as a hydrogen-burning star. A star larger than that suffers an even stranger fate. With sufficient force from gravity, the electrons in the core of a dying star are forced into nearby nuclei where they react with protons. This process, called electron capture, creates neutrons and neutrinos. The neutrinos radiate away, leaving a stellar object consisting only of neutrons, a neutron star. But without electron degeneracy pressure, how does such an object remain stable? A partial answer is exactly the same one as we had for electrons, since neutrons are also fermions with spin half. However, neutrons are not fundamental and can be chopped into smaller pieces, with every neutron composed of 3 quarks. So the answer is not simply neutron degeneracy pressure. Additional nuclear forces are at play, but not yet fully understood. As with all good science, there are mysteries yet to be solved. Recent measurements of a neutron star using gravitational wave astronomy weighed it at about 2 solar masses. Current theories suggest that the most massive neutron stars can be 3 solar masses. As beyond this, not even degeneracy pressure can save the star from the force of gravity. What happens when the gravitational force is so strong as to force the neutrons past known relativistic limits? That results in what are the most enigmatic objects in the cosmos, black holes. Before we explore the influence of quantum mechanics on black holes, we have to come clean on a few things. The stability of black dwarfs, the cold remnants of dead stars that are expected to fill the future universe. These don't collapse due to the degeneracy pressure explained by quantum physics and the Pauli exclusion principle. Electrons, like all fermions, just can't bunch up in the same place. You can squeeze and squeeze, but degeneracy pressure will resist that squeezing. It seems our future universe, filled with dead star hearts of degenerate matter, will be a very strange place indeed. But this is not the full story. While degeneracy pressure will become extremely important in the future universe, its influences are already felt all over cosmic history. There are already neutron stars in the universe, left over from earlier generations of stars that lived and died, many before the Sun was even born. There is one last twist to our story. We've mentioned that red dwarfs are the smallest stars, and they have a mass about 1/10 the mass of the Sun. But why are there no smaller stars than them? There are small clumps of gas that can collapse, and gravitational squeezing heats their cores. But as the matter gets denser and denser, degeneracy pressure rapidly comes to dominate, preventing further collapse. The cores of these stillborn stars are never hot and dense enough for nuclear fusion to ignite, and they, the brown dwarfs, are destined to roam the cosmos in the shadows. In fact, there is such a failed star in our very own solar system, the planet Jupiter. It had a different formation than a brown dwarf, but the physics is the same. The heart of Jupiter is about half the density of the center of the Sun, but more than 600 times cooler. The conditions are not extreme enough for nuclear fires, but its core cannot collapse any further due to the effects of quantum mechanics. Stop and think about that when you spot this majestic planet on a cool, clear night. In a few 100 trillion years, the last stars will have burned out. The universe will be plunged back into darkness. It will be filled with dead stars, radiating their remaining heat into the void as they cool toward absolute zero. Perhaps this is it for the universe, its end state in which it will exist for the rest of eternity. But as we will see, the action of quantum mechanics means that matter itself might eventually melt away into the darkness. Life is a permanent battle against decay, and without constant repair and upkeep, everything breaks down, be it your car, your house, or even your body. Decay is inevitable. But to the universe, at its most basic level, decay is an illusion. When food rots or iron rusts, chemical bonds bind and break, but the atoms that form the molecules and crystals that underlie matter remain unchanged. If we continue to break things down, to pull things apart, eventually all we will have are the individual atoms that make up all the matter in the universe. While atoms appear to be permanent, we know this is not truly the case. The elements were built up in the early universe and in the hearts of stars, and some of them can break down through the action of radioactivity. Some atoms indeed appear to be stable, resistant to the actions of radioactivity, and will last into the long, dark future of the universe ahead. But what of the protons and neutrons that make up the nuclei of atoms? How stable are these? It would seem that these too must be stable given that some atoms, containing protons and neutrons in their nuclei, appear to be completely stable. But if we take a single neutron, leaving it on its own, in about 15 minutes, it will be gone. A neutron can decay because it has slightly more mass than a proton. The mass difference is not much, only 0.1%, but it means there is enough energy in the neutron to be converted into a proton, an electron, and an almost massless neutrino with a little bit left over. This, of course, is the famous law of the conservation of energy. Energy cannot be created or destroyed, just transferred from one kind to another. Given this, there must be the same amount of energy before and after the neutron decay, no more, no less. What about a single proton? Does it decay like a neutron? Given that it is lighter, the proton cannot decay into a neutron, as this would violate the conservation of energy. There is simply not enough energy in a proton to be converted into a neutron. That is fine, you might say. Why doesn't the proton just decay into something else, something with less mass, so the decay will not violate the conservation of energy? The proton could decay into 1,000 electrons, and there would still be plenty of energy left over to make even more electrons. But when scientists watch and wait, observing individual protons, they do not decay into 1,000 electrons or 100 or even 10, all possibilities allowed by the law of conservation of energy. Before we get to how a proton might decay, perhaps it is worth stepping back and asking what decay even is, or more to the point, why it happens. Though our current understanding uses quantum physics in its full glory, it wasn't always so. Decay means to deteriorate, decompose, or rot. In the early 1900s, the systematic study of what they called radioactivity led Marie Skłodowska-Curie and her husband Pierre to find that the elements themselves are subject to decay. Some elements emitted radiation, but less and less over time. Whatever the source was, it decayed. It was discovered that such decay resulted in one element changing into another. In quantum physics, decay now means any process in which a high-energy state of a system moves to a low-energy state. Phrases you may have heard include, "The atom has decayed," which means it now occupies a lower energy state. But we know that energy is always conserved, so that lost energy must go somewhere. This is why all decay events result in some emission of energy. If a lower energy state is available, the system is unstable. A subtle distinction is made when the system in question is an unstable nucleus, such as that of the infamous element uranium. We call the process in this case radioactive decay because the emitted radiation is high energy and potentially dangerous. It is often called ionizing radiation because it contains enough energy to strip electrons from the material it passes through, which happens to have a negative effect on living cells in high doses. How much radiation a sample emits obviously will depend on how much of the stuff is sitting there. More of the sample means more decay, and less of the sample means less decay. Of course, we can't use this crude rule of thumb to make predictions. Luckily, the precise mathematical rule is only slightly more complicated. How much of a sample will decay in some instant of time is proportional to how much matter you have. This observation is actually quite remarkable. It means that over a fixed amount of time, the sample will decay by the same fixed proportion. For example, if it takes 1,600 years for a sample of radioactive radium to be reduced to half, it will take 1,600 more years for what's remaining to again be reduced to half, and so on. In this case, 1,600 years is called the half-life of radium. The half-life is a fundamental property of an element and is different for each type of element. Some elements, like hydrogen-7, hydrogen with 6 neutrons, have a half-life of yoctoseconds, a trillionth of a second, and others, like lead-204, have a half-life of yottaseconds, trillions upon trillions of seconds. This defines the stability of the element. A half-life of a yoctosecond means a very unstable element, whereas a half-life of a yottasecond, being millions of times the age of the universe, by the way, means the element is stable for all practical purposes. Now, you should be wondering how we would even know that the lifetime of an atom is millions of times the age of the universe. Did someone wait around that long to measure it? Of course not, but here is where quantum uncertainty comes to the rescue, yet again. Let's go back to radium and its 1,600-year half-life. If we have 1 gram of pure radium, radium-226 specifically, then after 1,600 years, we will have half gram of radium due to decay. But it's not the case that once the clock strikes 1,600 years, half of the radium decays. The individual atoms each have a small chance of decaying at any given second of time. After a second has passed, some have decayed, while the rest retain that same small chance in the next second. After 50 billion seconds, about 1,600 years, roughly half the atoms have decayed. Even though this sounds like a long time, we must remember that there are over a sextillion individual radium atoms in each gram. With a half-life of 1,600 years, this translates to 37 billion decay events every second. To put that in perspective, your body, which contains radioactive potassium, produces about 8,000 decay events per second. Yep, you are radioactive, as is your computer, your dog, and any piece of matter you can think of. The half-life is a number that tells us something about probability, not something real or physical. A given atom has a probability, no matter how rare, of decaying at any instant. If there are enough chances for a rare event, it will eventually happen. That's why spent uranium fuel rods from nuclear power stations are dangerous now and will remain dangerous long after humans have disappeared. So the question of whether protons last forever is really the question of whether there is a lower energy state they can occupy and what the half-life of decaying there is. Protons, being baryons, must decay into other baryons. That is, if baryon number is to be conserved. But like the other anomalies we have encountered, breaking this symmetry is a fun exercise for physicists. Sometimes, physicists break the mathematics of the current standard model to allow for proton decay, and sometimes completely different models meant to overthrow the standard model allow for it. There is an endless stream of proposals, but there is a problem. With every particle physics experiment, the standard model is vindicated, explaining the electrons, protons, and assortment of other particles that are spat out. With no cracks in its mathematics, many of the alternative proposals go into the garbage, while others sit and wait for the standard model to fail. Remember that the lifetime of a quantum thing, such as a particle, is a statistical question. If we say that the particle lifetime is 1 year, this means there is a 50% chance it will decay in 1 year. If it hasn't decayed in year 1, it has 50% chance of decaying in year 2, and so on. So while the lifetime of a proton may be staggeringly long, there is a chance, a small chance, that an individual proton might exist for only 5 minutes before decaying. If you watch a huge number of protons, say a swimming pool-sized vat of atoms and molecules, and know what the signature of a decaying proton looks like, namely the mysterious appearance of a fast-moving positron and other stuff, then you have a chance of witnessing one in decay. This is precisely what physicists have done, but so far, they have not seen the smoking gun of proton decay. Scientists are undaunted by the current lack of experimental evidence for proton decay and think it's just a matter of time before it will be observed. But what does evidence of a decaying proton mean for the future universe? After a few 100 trillion years, all the stars will have exhausted their nuclear fuel. Without starlight, the universe will descend into darkness, into a night that will last forever. The dead stars will exist in the darkness, cooling and fading into the background of the universe. But as we push out into timescales of 10 power 40 years, a mighty long time after the last star has been extinguished, the decay of protons will start to be felt. As protons decay, matter will start to melt away. In the darkness, the black dwarfs will evaporate into simple particles and light. After a few proton lifetimes, they will have dissolved completely into the nothingness. After protons have decayed away, the epoch of matter will be truly over, and there will be nothing but elementary particles and black holes inhabiting the universe. Of course, proton decay is not certain. Physicists think there are good reasons for protons not to be stable for eternity, related to the holes in our theories of quantum physics. But even if protons do not decay, it does not mean the universe will never change. Inside the dead hearts of stars, atoms will be squeezed very tightly together. This close proximity will very, very rarely allow for cold fusion, where quantum tunneling will meld atoms into new elements. This process will continue very, very slowly until all atoms are squeezed into a strongly bound atomic nucleus, iron 56. Without proton decay, after an unimaginably long period of time, around 10 to the power 1,500 years, all the matter in the universe will have fused into this eternal state of iron. If protons do decay, and once all the dead stars have melted away, other masses will still lurk in the darkness. Black holes, many formed from the collapse of stars and supernovae, will be impervious to the actions of proton decay, their matter locked up in their infinitely dense cores, a point mass that is known as the singularity, the name given to places in physical theories where infinity occurs. Physicists don't think the cores of black holes are true singularities. In fact, physicists think that the infinities of singularities have no place in theories about the actual universe, and something prevents them from existing. For black holes, it is speculated that the actions of quantum forces will ultimately prevent the formation of a point of infinite density, but the immense gravitational pull of the black hole will remain. Stuff that falls into a black hole is destined to remain there, and black holes will remain long after the last star has dissolved into the blackness. But will black holes last forever? Is the distant future of our universe destined to be an ever-thinning sea of elementary particles with a scattering of black holes? Within Einstein's general theory, black holes are truly eternal, able to grow by eating material. As matter falling into a black hole is on a one-way journey and can never get out again, black holes can never shrink. At least that's what everyone thought until the 1960s. It was then that a young researcher named Stephen Hawking began to ponder the nature of black holes. His focus was not the singularity, which is a mathematically confusing place to explore, but a region around the singularity known as the event horizon. The existence of the event horizon was known from the earliest mathematical explorations of black holes. Located at a particular distance from the singularity, the event horizon represents the no-way-back boundary. Things that cross the event horizon are compelled by gravity to fall into the singularity. Nothing can stop this from happening. No amount of struggling or rocket power can prevent this fall to the center once you are below the horizon. Strange things can happen at the event horizon. The bending of space and time means that light struggles to escape from just outside the event horizon, but at the horizon itself, light can be held motionless. For objects that fall into a black hole, an image of them, representing the last emission of light as it crossed into the abyss, is imprinted on the horizon. Hawking, an expert on relativity, wondered what would happen to quantum mechanical processes occurring at the event horizon. What would be the impact of a one-way boundary? Hawking's conclusion was extremely surprising, finding that quantum mechanics means that black holes radiate, converting the mass in the singularity into a faint glow at the event horizon. And the impact of this Hawking radiation on the long-term stability of black holes is stark. But to understand Hawking radiation, we first need to talk about the thorniest concept to come out of quantum physics: entanglement. Where there is smoke, there is fire. Where there is rain, there are clouds. Both of these examples are only correlations. It would seem even scientists constantly need to be told that correlation does not imply causation. For example, clouds do not always imply rain, and fire does not always imply smoke. It depends on what is burning. And in some correlations, neither event causes the other. A famous example is the fact that the number of crimes in a city is higher when the number of police officers is higher. Do police cause crime, or does crime cause police? In fact, it is neither. The population of the city accounts for both. A larger city has both more crime and more police. Population in this case is called a common cause. In the theory of causation, there are only three possibilities when it comes to a correlation between two events. Either the first event causes the second causes the first, or a third, unseen event caused both. But wait, how could the second cause the first? Is the future influencing the past? No. We don't need to see the events with our own eyes in the order in which they are caused. For example, we often see smoke before we see fire, but fire clearly caused the smoke. The only other important point about causes is taken from physics. The chain of events, from cause to event, must obey the laws of relativity. In other words, causes, like all transmitted information, are limited to traveling at the speed of light or lower. Let's imagine someone gives you and your friend a pair of gloves, but each glove is in a separate unmarked box. You're in Los Angeles, and your friend is in New York. You don't know which you have, a left or right glove. When you open your box, it turns out to be a left-hand glove. Now you instantly know that your friend's box contains the right-hand glove. If you repeat it many times, you either get a right or left glove. It's random, but there's a perfect correlation between the contents of the boxes because the person who prepared them knew what they were doing. Now let's think about this with electrons instead of gloves. You and your friend each have an electron in your box. You open yours and find that your electron's spin is up. At the same time, your friend opens their box and discovers their electron's spin is down. If you play this game many times, you'll see that sometimes your electron has an up spin, and sometimes it has a down spin. The sequence seems random, but what's not random is that you and your friend always get electrons with opposite spins. In real-life physics, we're not playing games, but this analogy helps us understand that even at the quantum level, seemingly random events can have a common cause. That common cause could be things like atoms or distant stars influencing the behavior of particles. This, Einstein argued, must be true to avoid what he called spooky action at a distance, meaning that one electron seems to influence the other from Los Angeles to New York. Although Einstein thought there must be a common cause, it wasn't at all clear what the common cause might be. It did not appear in the lab or in the mathematics. The common causes of quantum correlations thus came to be called hidden variables. But here is where things get really spooky. Hidden variables do not exist. There is no common cause for quantum correlations. In our game, the person who put the electrons in the boxes did not, in fact could not, know what you and your friend would find upon opening. In other words, it is possible to create correlated events that could not have been predetermined. We still know the electrons are correlated before their spins are measured, and this correlation is called entanglement. As far as the deep concepts in quantum physics are concerned, quantum entanglement is probably the most recent to be fully appreciated. It wasn't until the late 1960s that John Bell proposed an experimental test to prove that nature indeed behaves in this way. And it wasn't until the most recent decade that conclusive experimental evidence was provided, although it was done using photons, not electrons. While our cute little game suggests otherwise, manipulating and maintaining the states of entangled photons across large distances in the real world is an incredible challenge. But it is done, and we now routinely manufacture correlated events in the world that have no cause at all. Perhaps this is actually not surprising if you take the uncertainty principle to heart. The uncertainty principle taught us that some properties of quantum particles cannot be defined, that they do not exist before being measured. This certainly sounds like a handicap, both scientifically and technologically speaking, but it is not so. Entanglement is the basis for provably secure cryptography, a secret code that cannot be broken, and it can even teach us a thing or two about black holes. Before we get to that, though, we want you to do something. Toss an encyclopedia into a fire. Scientists would never condone burning books, but this is the best analogy we have. The encyclopedia, full of all sorts of good information, will of course burn. And after the pages burn up, all the information has been lost, or has it? In principle, we could collect all the smoke and ashes and meticulously piece them back together to recover the encyclopedia. This is yet another conservation law, the conservation of information. This law stems from the basic time reversal symmetry of the equations of quantum physics. Even if you toss the encyclopedia into a black hole, in principle, the information is still there, somewhere. In any case, there are many copies of the encyclopedia, so no real information has been lost. Consider the tragic scenario of your friend falling into a black hole with their unopened box containing one glove. We did not get to see what was inside, so that information is lost, right? No. The person who put the gloves in the boxes still possesses it. However, if it were the box with the electron in it, we have a problem. Since it is impossible for anyone to know what the state of the electron that fell into the black hole was, it seems the information is lost to the universe. This is the infamous black hole information loss paradox, where a black hole has no detailed memory of what has fallen in. And it gets worse. Suppose the entangled pair of particles in question is one of the particle-antiparticle vacuum fluctuations we met way back at the beginning of the universe. Further, suppose the antiparticle falls into the black hole, and the particle does not. The antiparticle then meets with a particle that makes up part of the black hole. These two particles then annihilate each other, and poof! There goes a little mass of the black hole. That is, black holes lose mass. They evaporate. What this means is that black holes aren't truly black, and through these quantum fluctuations and escaping particles, they glow. And as they glow, they steadily lose mass. This Hawking radiation is a feeble thing, with black holes emitting only a tiny morsel of radiation. A black hole with the mass of the Sun will take more than 10 to the power 60 years to reduce its mass by 1%. But Hawking radiation has a strange property in that the amount of radiation is inversely proportional to the mass of the black hole. This is mathematics speak for the smaller the black hole, the more intense the amount of Hawking radiation. So here we have a feedback loop. Due to Hawking radiation, a black hole will lose mass over time. And as it loses mass, its Hawking radiation increases, so it loses more mass, so its Hawking radiation increases. This runaway process continues, with the glow of Hawking radiation increasing until the black hole actually becomes visible. By this stage, the mass of the black hole is decreasing rapidly, and the intense radiation becomes ultraviolet, then X-rays, and then gamma rays, and then pop. The black hole has completely evaporated, and nothing is left. How long do we have to wait for a black hole to evaporate away to nothing? Much, much longer than the time it takes for all the protons to decay. For a black hole with the mass of the Sun, it is about 10 power 67 years, meaning that long after the last star has been extinguished, and long after the last matter has melted away into the background, every so often in the utterly dark universe, there will be a short, sharp flash of light as a black hole decays away. Supermassive black holes, with masses a billion times the mass of the Sun, are known to exist at the centers of the most massive galaxies, and it will take even more time for these to evaporate away their mass. These supermassive black holes might last for up to 10100 years, but their time will come, and they too will eventually vanish from the universe in a puff of Hawking radiation. Once the last black hole has decayed away and the final fireworks of Hawking radiation are lost forever, the darkness of a never-ending night will fall. It appears to be the end of all things. Or is it? Once all the dead stars have dissolved and the black holes have evaporated, there will be no more stuff in the universe. Well, no substantial stuff. All that will exist is an ever-cooling, ever-thinning soup of electrons and photons. The universe will be cold and uniform, and all useful energy will be gone. Without this energy, there will be no prospects for complexity and life. The universe will have reached its ultimate state, its heat death. The heat death sounds dramatic, but it was predicted long before modern cosmology with its fiery birth and expanding spacetime. In 1851, Lord Kelvin, whom we briefly met earlier, proposed that the universe was running down, cooling from hot to cold, with the eventual fate of heat death ahead of it. He was not the first to propose this idea, but he was the first to set it in the language of thermodynamics. We already considered the second law of thermodynamics when we were wondering why the universe was so similar everywhere and how it means that energy in a process is eventually minimized. We need to understand this in a little more detail, and to do so, we will have to introduce another concept from thermodynamics, namely entropy. An awful lot of words have been written about entropy and what it means. Words like disorder are thrown about, exemplified by the messiness of a teenager's bedroom. The concept of entropy can indeed seem messy and confused. This is not helped by the fact that there is not just one definition of entropy. Ludwig Boltzmann wrote down the first mathematical definition of entropy in the 1870s, an equation that now adorns his gravestone. At the same time, a slightly different formulation of entropy, based upon probabilities, was written down by the American statistician J. Willard Gibbs. The two sets of mathematics look very similar, but there are occasions when the answer you get depends upon the mathematics you choose to use. Obviously, this is not ideal. Both Boltzmann and Gibbs were interested in thermodynamics, the flow of heat in a process, which was born out of a truly practical problem during the Industrial Revolution, namely determining how efficient a steam engine can be. It then grew into an edifice of modern science that has occupied the minds of top physicists ever since. A student in high school might first encounter thermodynamics in the form of the gas laws of Boyle, but once they get their teeth into the subject at college, it becomes statistical physics, examining the different ways that atoms in a gas might be rearranged to produce similar or different outcomes. At its heart, though, thermodynamics is a study of the flow of heat. A neat way to think of the entropy of Boltzmann and Gibbs is to consider the amount of useful energy in a system. Useful here means that the energy can be tapped to do something, such as run an engine or power a living being. Things that have lots of useful energy are at lower entropy than those at high entropy. Notice that it's not the total amount of energy that is important, just the amount of useful energy. You might be scratching your head over this a little, so let's think of a simple example. Imagine you have two blocks of metal, one hot and one cold. If you connect the two, heat will flow from the hot block to the cold block, and you could theoretically use this flow of energy to power an engine. So the situation with a hot block and a cold block of metal is at low entropy as there is energy that can be used. If, however, we have two warm blocks containing the same total amount of energy as the hot block and the cold block, when we connect them, no heat flows between them and there is no useful energy in the system. The two warm blocks are at higher entropy. This might seem a little esoteric, but in fact, we can think of any process in terms of its flow of energy from one place to the other. Humans experience the flow of heat, the energy that powers our everyday world, as an irreversible process. Shown a video of a food cooking, an egg cracking, or a vase breaking in reverse, we immediately feel a sense of dissonance. But show someone a video of a ball arcing through the air, and they will not be able to tell the difference between forward and reverse. All our tried and true laws of physics are reversible. Play the laws of physics in reverse, and they are still solutions to the equations. The laws of physics are time-symmetric. But how can it be then, if, according to the laws of physics, going forward is just as good a solution as going backward? Time flows in only one direction. This paradox is probably the most obvious and simplest to state unsolved problem in physics. The so-called arrow of time gives a memorable name to the idea of the asymmetry of time, that it has a definite unidirectional flow. This idea is at odds with the equations of motion of Newton, Maxwell, Einstein, and even Schrödinger, all of which are time-symmetric. There is one irreversible process in quantum physics that we haven't mentioned yet, though, and that is observation. Heisenberg's uncertainty argument that measuring one property of a system can unavoidably affect another. Heisenberg's example was position and velocity. A more extreme example is measuring the position of a photon by absorbing it, and hence completely destroying it. This doesn't sound all that reversible, does it? In fact, the technical name for the mathematical operation of measurement is collapsing the wave function. Today, when an unwitting undergraduate physics student is introduced to quantum physics, they are presented with the postulates. These are the rules of quantum physics stated in a concise and bite-sized way, far removed from the tumultuous path that actually brought us here. The three main postulates. 1. When a physical system is prepared, it is mathematically described by its quantum state, the wave function. 2. As time passes, the quantum state changes according to the Schrödinger equation. 3. When a measurement is made, the quantum state immediately becomes the one associated with the outcome observed. Really, the first and the third are essentially the same if you imagine filtering out the outcome that you want to prepare the system in. Still, we are left with two different ways things can happen to a quantum state. The Schrödinger equation we met earlier is the bedrock of quantum physics. It is time-symmetric and unambiguously applied. The collapse is another beast altogether and the cause of great strife in the foundations of quantum physics. For the practitioner, it is obvious when to apply it, when a measurement is made. However, for a third party, it is not so clear. When exactly is the measurement made, and who qualifies to make one? Must it be a scientist? Does nature itself measure quantum systems? All these questions encompass the so-called measurement problem. Since all the successful equations of motion in physics are reversible, physicists generally do not like the fact that the seemingly violent collapse of the wave function is irreversible. It's a problem with the theory, they say. Why is it still there then? Well, it works, and does so with astonishing precision. But there also is no consensus on which process is more fundamental, the Schrödinger equation, or the measurement. If we accept that collapse is a real part of the physics and not some artifact we haven't figured out how to get rid of, then we have found a source of irreversibility. But not so fast. After all, you, the thing doing the measuring, are made of atoms and thus must be described by quantum physics as well. Indeed, to measure something is to interact with it, and interactions are again described by the Schrödinger equation. We've come full circle. The task of 20th century quantum physicists was to either come up with the precise location in which the quantum state collapsed or show that the reversible dynamics of the Schrödinger equation can lead to increasing entropy. More than 100 years later, we still cannot say when and where the quantum state collapses. If we take an operational view of quantum physics, a view that presents the theory only as a toolbox for practitioners, then we can trace the collapse to some internal update happening in the mind of the observer, or an observer observing an observer, or, well, you get the picture. Luckily, the second path has provided some fruitful answers in a disguise we have seen before: entanglement. When two systems interact, they generally become entangled. The nature of entanglement means all the information is carried by the entire system, And, in the extreme cases, the individual systems contain zero information. As systems continue to bump into one another, entanglement builds and builds until we reach the point that any particular part of the system possesses zero information. To connect this back to thermodynamics, consider that one would certainly need information about a system in order to extract useful energy from it. While a more formal connection between thermodynamic quantities like energy and heat can be made, the crux is just that: no information, no useful energy, maximum entropy. Now, that quantum system could very well be the universe as a whole. In other words, the universe, taken to be one big quantum thing composed of smaller quantum things, ends up a big entangled mess. Even in the quantum realm, entropy increase marches on, pointing steadfastly in the direction of the arrow of time. No matter how many times physicists have tried to reverse the arrow of time and explore the origin of our universe, theoretically anyway, we keep coming back to Kelvin. The fact that everything is running down goes right through the heart of physics. Our universe was born with lots of useful energy, smoothly distributed matter with the potential to collapse into stars and light elements with the potential to undergo nuclear fusion into heavier elements. Why our universe was born with its abundance of useful energy is a mystery, but every moment of every day, this useful energy is dwindling. Even you reading this page is processing lower entropy energy, probably from that yummy burger you had for lunch, into higher entropy, less useful energy, as the infrared radiation emitted from your glowing skin. This process continues forever and is irreversible. Once the last proton has decayed and the last black hole has evaporated, Kelvin's nightmare of a cold, dead universe will be inevitable. Perhaps the universe will have entered its final state, and that's all there will ever be. But perhaps not. The universe might well be reborn. And the secret ingredients to allow it to do so might be dark energy and the quantum,